In this video, I want to have a look at some examples of problems that involve our double angle formulas. So our first example asks us to simplify sine 2a cos a minus cos 2a sine a. So we can expand out these two terms here using our double angle formulas. So that's going to give us 2 sine a cos a, and that's still multiplied by this cos a that was on the end there. And then we're going to have minus, now cos 2a, we're going to have to put brackets in because that is the same as cos squared a minus sine squared a. And that's multiplied by our sine a. So I'm now going to expand this bracket over here. So this whole front section is going to stay the same, except we're going to simplify that cos a to be a cos squared a. Then we've got that minus, we'll have cos squared a sine a. Now just be careful, you do have this negative out the front, so that negative times the negative would give us a positive, and we're multiplying by the sine a at the end, so we'll end up with a positive sine a cubed. All right, so then our first and second terms are like terms because they both have that cos squared and sine, so we can simplify that to sine a cos squared a. And then we've got our plus sine cubed a. Now if we factorize that, we can pull a sine a out the front. So we'll end up with a cos squared a plus sine squared a. And we know from our trig identities that cos squared plus sine squared is just 1. So this whole bracket becomes 1, which will just leave us with sine a as our simplified version. Our second example asks us to prove that sine 2a over 1 plus cos 2a is equal to tan a. So we're going to start with the left-hand side. Now that's sine 2a and cos 2a, I'm going to expand those out using our double angle results. So we'll have 2 sine a cos a on top. And then we'll end up with 1 plus cos squared a minus sine squared a. All right, now in that denominator, that 1 and the minus sine squared a, we know that 1 minus sine squared a, that's the same as cos squared a. And that's that rearranged version of cos squared plus sine squared equals 1. So that means that denominator is just going to give us a cos squared a plus another cos squared a. So we'll end up with 2 cos squared a on the bottom. Okay, now we can go through and simplify. So if we divide top and bottom both by 2 and divide top and bottom both by cos a, that will simplify down to sine a in the numerator and cos a in the denominator, which we know that sine over cos is equal to tan, and that is our right-hand side. Our last example asks us to evaluate cos of 2 sine inverse root 3 on 2. Right, so to do that, we're actually going to let alpha equal that bracket. So, sorry, not the whole bracket, just our inverse function. So we're going to have alpha equals sine inverse of root 3 on 2. Now we know that we can rearrange that then to say sine alpha equals root 3 on 2, but that only works within the domain. So when our alpha is between minus pi on 2 and pi on 2. So to solve this, we're going to draw up our all stations to central diagram. We're only looking between minus pi on 2 and pi on 2, and we know that it's positive. So we're not looking at these ones at all. We know that it's positive, which means it's going to be in this quadrant here. This is our alpha. And then we've got our root 3 on 2, which means this side here is root 3 and our hypotenuse is 2. If we go through and do Pythag, then we know that this third side is going to be 1 unit long, or you can know that from your special triangles. All right, so once we know that, then we can look back at our original problem. So this cos of 2 sine inverse of root 3 on 2, that's going to now be cos of 2 alpha. Now we can figure out what that alpha is. Sorry, we can go through and expand that to cos squared alpha minus sine squared alpha. Now using this triangle, cos alpha would be a half. So that's going to give us a half squared. And of course we know that sine alpha is root 3 on 2. And we're going to square that. So that's going to give us 1/4 minus 3/4, and will give us an answer of -1/2. Okay, so that's having a look at 3 different examples of problems involving our double angle formulas.